Good evening. My name is Venkatesh Subramanian. Uh, I am doing my MBA in Financial Planning and Analysis in Arkansas State University. Today is Monday, 28th of October, evening around 6:30 p.m. Eastern Time. This video is a recording of my presentation of chapter one, which is the introduction to cryptocurrencies, cryptography and cryptocurrencies, in the course seminar in finance. So, without further ado, we will go into the presentation. So, yeah, as I said before, chapter one, introduction to cryptography and cryptocurrencies. So, agenda. What are we going to cover today in this session? The first part is a simple definition of what is cryptography. What does that comprise of, and what is a cryptocurrency, which is sort of a derivative of cryptography. Cryptography is a technology, and cryptocurrency is a one of the implementation, one of the uses of cryptography. So, and we will further dive into some more technical concepts of cryptographic hash functions. So, how is cryptography achieved? So fundamental concept is a cryptographic hash function, and then further dwelling into it would be hash pointers, data structures, digital signatures, public keys as identities, and we will finish with a simple cryptocurrency model that was originally defined, and a final summary of what we discussed in the chapter. So let's go into the first topic, cryptography and cryptocurrencies. Okay, what is cryptography? Cryptography is basically the study of uh, transfer of data between point A to point B. And this is digital information, right? To put in very simple layman terms, it talks about, or it is about the study of transacting digital information from point A to point B, or person A to person B. So, however, this is not as simple as it sounds. What are some of the key elements here? In the modern world now, there is a lot of very, very secure, important information that is being transferred or secured or between two different parties, right? So, keeping that in mind, there are several key factors that need to be discussed here. Step one, right, is when you actually transfer the data from point A to point B, there should not be a third party that can intercept the information. Let's say, for example, if this is a very critical information that should not be, released out to anybody outside of those who it is intended to. So encryption is one of the key concepts, right? How do you basically modify the data in an information that is not human readable, that's not human understandable, and how do you transfer it through the pipeline between point A and point B? So that's encryption, right? So how do I modify the information and send it out? And likewise, on the other end, if it's not human readable, or if that information is not easily digestible, then point B at the destination, the same challenge would exist, where it is going to be hard to understand the information that's passed via this channel. So obviously, the subsequent need is a good decryption technique, which is on the receiving end, where the information that gets passed is decrypted into a understandable format or a meaningful information. Basically, how do we translate it back to the meaningful data? So that's the decryption concept. And number three, integrity. So this also talks about another element of data transfer. Like, let's say, for example, if information is passed from point A to point B, which says, say, for example, if this packet weighs 3 pounds. This is just logically, this is just a way of logically understanding the concept, and not necessarily very practical. But like, let's say if the information that's translated says this package weighs 3 pounds, um, it is also possible that somebody in between could not only intercept the data but also modify it. they might modify it to like this package weighs 5 pounds. So now the actual information, the integrity of the information that's being transferred between point A and point B are lost. So how do we also maintain the integrity of the data is also a key concept here. Likewise, the last element here, talks about authentication, which is if point B gets data from point A, how does point B know that this is truly from point A? How does and likewise how does point A specifically address it to point B? So there are authentication methods, authentication techniques that help drive information reach from the proper source to the proper destination through proper encryption methodologies, and also making sure that the data integrity is maintained. So how do we do that, right? That's where we get into some of these algorithms and mathematical computations and practices that allow or that have been built to successfully accomplish this. So what are some, the last point here talks about what are some of the practical uses. There are several practical uses that even, some of us might be using cryptocurrency and are into cryptocurrency, and, some others may not even use cryptocurrency, but there are real practical uses that we use on our day to day. For example, like digital signature. So there is a lot of key applications here, where, somewhere between like signing contracts. If you're working business to business, and there are contract documentation that gets signed and sent over, so which have legal implications, right? So that's a good example. So digital signature is one, and obviously, like I said before, the primary focus on this chapter is how is this cryptography used in currencies, that is cryptocurrencies. That's one of the key applications of cryptography, which is cryptocurrency, which we are going to talk in detail in a bit. So cryptocurrency is one of the applications, and then there are several others, but another key application here would be secure online data transfers. And another everyday application, that we use in our home is we have a lot of different smart devices. You know, I don't want to name a specific brand, but there are several different smart devices that actually talk between each other, which we famously call as IoT, Internet of Things. Even Internet of Things uses this technique to allow some of these devices to talk between each other, basically transfer data between each other. So in a world that's fastly transforming from a data standpoint, the cryptography and cryptocurrency, like key concepts, are very very pivotal from a business evolvement standpoint. All right. So jumping on to cryptocurrency, cryptocurrency is one of the applications of cryptography, and it is, in some places it is accepted. In some areas, it is still in a trial phase where people are still, apprehensive, and rightly so, because cryptography has its own advantages and also challenges. So, what is cryptocurrency? Cryptocurrency is basically a digital currency. This is not real cash like, dollars or any other standard currency. So, this is all 100% digital, and there are several platforms that are offering different kinds of cryptocurrencies, like, Ethereum, Bitcoin. There's just a lot of different platforms that provide these cryptocurrencies, and each platform have their own algorithms and their own techniques on how the currency is maintained. Um, and just to baseline, pretty much all of these digital currencies use cryptography technology or technique. And primarily the fundamental model started off as a single ledger, which is a single source that controls all of this data transfer and information. And obviously that has its own set of challenges. Therefore, this has evolved into a distributed ledger, meaning all of these, the ledger, basically, for lack of a better term, like a general ledger in financial terms, this ledger is distributed across a network of several computers or several systems that actually maintain the same set of information, which is tracked through different techniques. So what does that do, right? It basically decentralizes. So you've mitigated risk where if all of this information is in a single source, it can be easily compromised. And in some situations, if a disaster hits, then we lose all of the information and all of the currency that people might have gained over time. So having a distributed network, having a decentralized network, basically mitigates some of that risk, and also it enables pseudonymity and also ability to rapidly transfer data between different systems, and also it gives you more flexibility in terms of programming and building the systems. So hopefully that gives a good basic understanding, or at a fundamental level understanding of what is cryptography and how is it used in cryptocurrency. So with that, we will also move on to the next slide here, which is a very primary concept of cryptography. And mostly in this chapter, we will be primarily focusing on all of the technology or mathematical models behind a cryptography. And at the tail end of the chapter, we will briefly discuss about how the cryptography is used into a cryptocurrency. So a cryptographic hash function. So what is a hash function in general software or programming terminology? A program or a function, as in simple terms, is you feed an input and it goes through an algorithm which does certain calculations and then spits out an output. So that's fundamentally what a function means. As far as cryptography goes, the fundamental layer here is called as a hash function. So what is this hash function? What does it comprise of, right? And some of those bullet points are geared towards explaining what does that mean, and how it is utilized. So as it suggests here, like if you pass the same input to the hash function, pass in, the output is always going to be same, right? So same input is always providing same output. And also hash functions are pointer based, so which means the processing speeds are really fast. Uh, and faster the input is fed into the system, the outputs are faster, and that enables fast transactional speed. And particularly in an arena where we are um, transferring currency, transferring money, the efficiency becomes a very, very critical factor. Therefore, hash functions play a very vital role in terms of uh, transferring this information and making sure it's speed and fast and efficient. So some of the key functions is it is also considered as a one-way function, which means the hash, or like the converted, the decrypted, encrypted value of a particular function of a particular input will never be the input itself. So for example, if we pass input as Venki to the function, the output of the function will never be Venki. It's going to be in an encrypted format. And typically there are several hash functions, in which which we'll talk here in a second. Some of them are like 128 string long, 256 string long, so on and so forth, and which is also evolved over time. And likewise, there are a couple of other elements here, like hash of two different inputs will not be the same. So if you're passing two different inputs, it cannot have the same output, and for logical reasons, right? So if the encrypted value is the same for two different inputs, then think about what happens during decryption. There is a possibility of incorrectly decrypting that information, right? I pass input as A. If it gets encrypted into a hash value, let's say 123, and if I pass input value B, which also encrypts as like 123, on the other end, the information, there is a challenge of whether it should decrypt it back to A or B. So obviously, the hash of two different inputs does not give you the same output. Likewise, any small changes to the input significantly changes the output. And the reason behind this is to make it even more harder for people that are trying, or for elements that are trying to crack this data or intercept this data in its path. So the more and more that means, in order to like decrypt this, decode this, it's just probability wise, it's going to be more and more challenging and more difficult. So some of these fundamental or key characteristics make cryptographic hash functions work in a cryptocurrency. This is why it is a very efficient model in cryptocurrency. And also, over the past several years, the hash function algorithm has evolved, which is what we're going to see in the next section here in terms of common hash functions. So a very basic one was like the MDA5 message digest algorithm 5, which is a 128-bit based algorithm. And in simple layman terms, 128 bits, a bit is equal to a character. So whatever input gets passed, it basically spits out 128 character per input function, right? And over time, it was proven that some of this can be cracked, some of this can be decrypted. Therefore, the technology evolved. It evolved into several other algorithms like SHA-1, SHA-2, and majority of these are like from a 128-bit to it has evolved to a 256-bit algorithm. So which thereby making it far more difficult to crack, far more difficult to uh, decode. So that's the fundamental of cryptographic functions. And now moving on, the next slide talks about hash pointers and data structure. So this is again, more detailed technical concepts. So if I have a hash value, and this basically further talks about efficiency or speed of processing, right? So all these hash data, has an address, as a digital address. And the digital address is nothing but the pointers. So every transaction in the system belongs to a very specific pointer block, and thereby, um, if a particular input data has been encrypted, has been run through a hash function, it gets stored in a particular location, and the location has a pointer. So therefore, anytime the data gets changed, then the locator or the hash pointer changes. So this helps maintain the integrity of the data. One of the concepts that we talked about in an earlier slide. How do we maintain integrity of the data, right? So this hash pointer and data structure concept actually helps maintain the integrity of the data. So once after an input goes through a hash, it gets stored on a certain block, which is, think of it as a memory in a computer, in a digital environment, where there is a little block, and that block stores this information in an encrypted format. That particular block has a specific address or a pointer. So that's nothing but your hash pointers. And then anytime if the data gets tampered or changed, it also changes the pointer, which basically acts as a identifier of whether the data has been tampered or not. So maintaining the pointers as a second layer of support makes sure or helps prevent data tampering. So, going back in here, right, it's a unique identifier that points a location. And why is it required? It is required to make sure that the location of the data has not changed. And, what are our benefits? Obviously, like this is a block, and so it makes sure that the data is not changed and it's tamper evident. There are several again enhancements on this structure, which basically talks about Merkle trees, which is a tree with hash pointer. So think of it as not a single block. It's a tree of multiple blocks where it sort of builds like a parent-child relationship. So one way to visualize this would be a genealogy, a family tree, right? So likewise, how does one data relate to another data, and how all of these are interconnected to each other? So think of a piece of data encrypted in a format in hash as a block, and likewise there are several blocks. So how are all these blocks connected to each other? So in some sense, this leads us to the terminology or leads us to the concept of a blockchain. So how is all of these interconnected with each other? So that's basically in the form of in Merkle trees is basically a form of a tree-based structure. Moving on, right? So, okay, so what are some of the key, again, concepts? It all basically talks about your encryption. We talked about encryption. We talked about decryption in the form of, we talked about data integrity. So we touched on all these three concepts so far, right? The encryption and decryption are taken care of by the hash pointers and, basically, hashing the data, and then the integrity of the data is managed by the hash functions, and the integrity of the data is managed by the hash pointers. So now we talk about authentication, which is how do we make sure that the information, if it comes from point to A, how do we make sure that it does come from point A, right? So that's where some of this digital signature concept comes into picture. So again, no surprises here. It talks about like every sender and every receiver have their own private keys, private identification, and also they have like public keys that they would share with others that they are transacting with. So this conceptually, this is what drives the authenticity, or basically making sure that the information is truly from the source and it truly hits the destination. So how does this break down, right? So the digital signature, obviously, it helps identifying the person that actually sends the information is by identifying this signer, or the data source of the data. And also, again, further it helps prevents data tampering and modification during transmission. And also, once the destination it hits, right, this is very unique to every single user on the network. So which means if it comes with your specific signature, again, which is also there's private keys, and then there are public keys. It has your private key stamp. So if it was truly sent by the sender, that person cannot deny that this information or this currency did not, the transfer did not initiate from that individual or that user. Okay, so what are some of the different techniques, right? Likewise, just like the hash pointers and hash algorithms, the technology sort of evolved with digital signatures also, and there are a few evolution that's talked about on the sheet here. RSA being the fundamental digital signature, and from there it evolved into the elliptical curve and elliptical, digital signature, which is also called as the Edwards curve, digital signature algorithms. Okay, so what are the real world implications, right? I mean, this is all technically, a lot of things happen in the background, which is great, but where is it used in real world? And this is again everyday common application, starting from email transfers between people uses digital signatures, right? These are some things that we see day in and day out. Document signatures, like contracts, certificates. If we do online certifications, you get a certificate from a certifying agency and a certifying authority. You get a digital signature, right? So all of these use digital signature technique, and obviously, last but not the least, legal agreements between major, organizations, corporations. All of it's now digital. The transactions are not paper-based anymore. They're all legal. They're all digital, and so great benefits that come along with it. Okay, and how does this impact, or how does this involve in our cryptocurrency? Kind of going back into how the cryptographic technology is used in cryptocurrency. This is next is the following advantage. So blockchain and cryptocurrency. So this again is helped in validating the ownership of the information between the sender and the receiver. So we've talked extensively on that. What are some of the other uses? System firmware updates. It could be your ranging anywhere from smart devices to laptops, and several devices that are connected on a network. The firmware updates make sure that like say for example, if you're using a Microsoft based device, there is technology. This technology is used in the background to make sure the updates that are being sent to the devices are truly from the Microsoft source in this example. Likewise, we also touched on the IoT, or when smart devices talk to each other, how do we make sure that the security and integrity is all maintained? Again, through digital signatures. All right, jumping on public keys as identities. So, like I said before, there is secure transfer of data. So, between, for example, if it's involved between two different parties, there is a private key that usually identifies that particular party, and it's not shared. It's generally decentralized and stored in the network, but it's not stored as public information. However, there is also public identities that can be shared to the other party that you're trying to transfer data or trying to transfer currency with. So that's one way or mechanism to make sure that party B knows that this is party A knows this is party B, and they can effectively manage identity without compromising the integrity or the challenges that come along with it. So, public keys serve as identities, and user can create several public keys without the central authority. What are some considerations is like, creating identity as anonymous, and, so private public keys that are generally shareable kind of gives you real world identity as who this person is, and, further information into the individual. So those are some considerations with the public keys as identities. Okay, so now that we've touched all of these concepts, how does this play into a cryptocurrency? So, what is a simple cryptocurrency? It's a digital token. It's a digital currency that can be transferred between two different users. And just like any other standard conventional currency, there is fixed supply, and therefore a digital cryptocurrency also goes through inflation, deflation. The value of the currencies goes up and down based on the transactions, based on how fluid the currency transfers are. And obviously, like, it's 100% digital. There is no physical paper or no, it's all 100% digital. And likewise, conventional currency is generally centralized, right? US dollar is generally printed and controlled by the US government. Likewise, every country have their own reserve banks that monitor and that control the currency. Whereas the one of the key sort of advantage as well as disadvantage of cryptocurrency is that it's decentralized. It is not limited by a geography. Users across the globe can be operating on a centralized currency, thereby eliminating any differences between currency, and bringing everyone in a standard platform. So, what are some of the types of cryptocurrency, simple cryptocurrency, as described in the book? Initially started off as what's called as a goofy coins. And in this term, goofy is basically the central authority that has control over this currency that gets distributed to different people. If there is a central authority, and if there is a authority is not a good thing. It can be a good thing in some ways, but there are certain challenges that come with it, right? One of the major spending is if I have a particular cryptocurrency transaction, I can certainly issue to two different people, and there is no governing body that kind of controls the central authority's ability to only transact a particular currency with one individual and not the other. This is the prime fundamental challenge with it. Therefore, that brought up to like the need for decentralization. Likewise, the further enhancement to that is the Scrooge coins. And again, this also generally centralized, but at least what happens is, this has an append only ledger. So basically what it means, there is more technology put into it that prevents the central authority from issuing a single currency to multiple different parties. However, both the simple cryptocurrencies fundamentally are based on central authority, which is no different than any general conventional currency. And this being digital has further challenges. Therefore, it took the cryptocurrency into a further new era of decentralization, which is nothing but the Bitcoin, which basically decentralizes this authority concept and brings in a distributed ledger environment. So everybody is accountable, and minimizes some of the frauds and challenges that come with the centralized authority concept. All right. Having said that, we hit the summary here. Cryptography, obviously offers several advantages, which is the key one being decentralization and generalization of a currency across geographies, and increasing purchasing power and spending power for users across the globe. And also, obviously, this is shown in cryptocurrency's ability to grow and gain significant attention. However, it also comes with some key drawbacks, which is technologically it's still growing. There are still drawbacks. There are still challenges that needs to be addressed. And obviously, one thing we established in this discussion is decentralization is key. And obviously Bitcoin is the decentralization concept that basically is built to handle some of the challenges and also work on the fundamentals of a cryptography concept. So that summarizes uh, this chapter. Yeah, and thank you for listening in, and hopefully this information was helpful. Thank you so much.